Okay, hello. Let's continue with the polynomial functions. This time we're going to deal with odd degree functions, polynomial functions. So we're going to deal with the degree 3 and degree 5, the cubic and the quantic, and then we're going to talk about their graphs and all the characteristics of them. Okay, let's start off with the general form of each. So we'll start with the cubic function. There's an x cubed term in there, and the leading coefficient. So this is x cubed in there. The leading coefficient a needs to be there in order to make that a cubic function. All right. So let's go to the graph. Let's go to Desmos and look at some of the possibilities. So here is the general form of the cubic function. I created a slider for all the leading coefficients, including the constant term d. At the beginning, I like to set everything equal to 0 except the leading coefficient a, so that I can create a parent function for a cubic function. And a parent function for cubic, I just want to make a note here. The parent function is f of x equals to x cubed. This is the parent function. Okay? For a cubic, that's a parent function. And well, we're added for the parent function of the quantic, it's x to the 5th. Okay, so that's the parent function for the power of 5. But let's go back and continue with the cubic. All right, now as you can see, the end behavior is the first thing. Quadrant 1 and quadrant 3. That's where you see the end behavior right there. Simple as that. Now, regardless of what we can do with this curvature, there's a curvature change that is happening. The turn is happening. There are two turns, if you can see. One is in here that is coming in, and there's another one in there. So there are two turns happening, two curvature changes. And in this case, because it's the simplest form, there are no other quadratic terms, because that's 0, no linear term, that is 0, and no constant term, and that's why you get the most simplest form. But look what happens. So based on these values, the leading coefficients, you can see different number of x-intercepts. So right now we only have one x-intercept. Okay, now it turns out that so it has to cross the x-axis. That's one of the characteristics of the cubic. It has to. In fact, you can see the same characteristics with the quantic function as well. But then as we move a, so I'm going to leave a to be 1, but we're going to move others. So let's move b right now, and notice what is happening. So what is happening is that the quadratic term of the cubic polynomial is now becoming more defined, and as that happens, there is a quadratic. So this graph that you can see right here, that looks like a parabola, that is the quadratic term right there. That's a component of that. Okay, and as I move it to the positive, the positive, the other side, notice that that actually flattens out more and more because it's becoming closer to 0. All right, and then based on that, I can change. If I change c, let's see what happens. Okay, so when I change c, it also straightens the graph, okay, the linear term. But it also, look what's happening. It goes from the intercepts of being 1 to 2, and then to 1 again. Okay, and then based on what d is, you can see what is happening. Then d, if you remember, basically you're moving the graph up and down, the part of the function transformation. So that's what's happening. So look what happened. Look what happens when we move the graph up completely. So the function crosses the x-axis. Great. At how many times crosses it? 1 time. And this is the x-intercept, or the root, or the 0 of the function. Okay, as we're coming down, notice that I can actually make it that it touches the graph only at 2 places right there. That's only 2 places. One is in here, the other one is in there. So we could have 2 possible x-intercepts, or 2 zeros, or 2 roots. Great. Now if I move it down more, let's move it down more. Now we're going to have 3, and then based on that, I can move around and really make the graph, the curvature of the graph, profound, the turns more profound, and peaks and valleys are more profound. And you can see easily there are 3 possible intercepts. Now here is another question. in terms of the maximum and minimum. Does this graph have maximum minimum? No, it doesn't. It has a relative minimum and relative maximum, but that's not what you need to know for the purpose of this course. That's calculus. All right, but other than that, that is basically it. Actually, one more thing before we do the notes. I want to make sure that what happens, I want to make sure that you see what happens if a is negative. So look, it is, well, it's negative, like a negative 0.4, but it doesn't matter. But you can see what has happened now. The end behavior has changed. It's not from going from quadrant 1 to quadrant 3, is now quadrant 2 to quadrant 4, okay? Now again, it's the reflection over the x-axis. We've talked about that on the function transformation. When leading coefficient is negative, that's what happens to the graph. All right, now we can go ahead and include that in our notes. Okay, here it is, end behavior. If a is positive between quadrant 1 and 3, if it's a negative, that means reflection over the x-axis, quadrant 2 and 4. And then the domain, all real numbers, range, all real numbers. We could see that on the graph. Okay, you can go back and double check. And then another point is that there's no minimum or maximum value of the function. All right, and then the number of the x-intercept. Possible numbers, 1, 2, and 3. 1 is the minimum number of zeros. We showed that. There is a possibility of 2, and then there's a 3, maximum number 3. What you do not ever gonna get is not possible. That would be zero intercept. The graph will always have to come down and cross the x-axis at one point, okay? And that is what that is. All right. What I want you to realize as well is that this maximum number of zeros, again, 3, matches the degree of the polynomial, always, all right? But in this case, this odd degree polynomial is giving you 1 as a minimum number of 0. Let's see if the same thing happens for the quantic function. So here is the quantic function. General form, parent function is x to the 5th. Let's look at all the end behavior, domain, range, and number of intercepts. Let's go to decimals. So here is the general form of the quantic function. And it turns out that, so I put all the sliders in, but with the basic one, which is x to the 5th, and where a is 1, it looks like a cubic, almost like a cubic power of 3. And I put it in there as a cubic. Look. It's just that the cubic has got more curvature change, as in more profound curvature change. But quantic is pretty much like that. It just is a bit flatter, but depending on what B and C and D is, we can change that. And look what is happening as I change that. So the quantic, again, crossing down the end behavior, quadrant 1 and quadrant 3, and depending on what B is, so let me move the B around. So here's what I'm doing with the B right now, okay? I'm moving it around, and notice that when I move B, you get how many x-intercepts? You get possibly 2, 3, so 1, 2, 3. I can move it, I can get maybe 1 and 2 if I touch the graph. As I move the B just enough, I can do that. And then notice that it can change, right? And it goes down. There is a curvature change. That's the quartic term of the quantic function. All right, so that's what that is. And then let's see what happens as I move C around. Okay, when I move C around, it's a little bit changing. The cubic function part of that, the cubic term of that changes a little bit depending on what that is. And then let me go and put that back at the 1. And then notice that what happens as I am moving B or C in a different direction, and you can actually go ahead and play with all of these, and you realize that as you're playing with these, you can move the graph up and down, and you can see the possible number of zeros, but always the graph is going to cross the x-axis. Now I want you to see this specific quantic function. Okay, how many x-intercepts do you see? 1, 2, 3, 4, 5. 5 x-intercepts you see there. And then depending on, and in this case, we don't have a x to the 4th term here. We don't have also the dx squared term is not there. But again, what you can see is that the maximum number is 5 again. The minimum is 1. And then this graph also, this quantic function also doesn't have a maximum minimum, okay? So now, depending on the graph being positive or negative, the leading coefficient, again, it flips over the x-axis, and that would change it. So the end behavior of the graph, if I were to zoom this closer, you could see that the end behavior of the graph, let me get off the line. The end behavior of the graph is always the first and third, if it's first quadrant and third quadrant, and then if it's flipped, second and fourth quadrant. Okay, so let's go ahead and now put all that on the note. In the notes we have, here it is, the end behavior: a positive leading coefficient, the quadrant 1 and 3, negative quadrant 2 and 4, domain and range, all real numbers for both, and then the number of x-intercepts. In this case, you get 1, minimum number of zeros, 5, maximum number of zeros, and by this time you should see the pattern that the maximum number of roots, x-intercepts, zeros of any polynomial is the degree of that polynomial. Okay,